So it's my great pleasure to introduce Mark Raasveldt, who is co-founder and CTO of DuckDB Labs. He is also the lead developer on the DuckDB database system. Prior to DuckDB, Mark did his PhD at CWI, and he's also currently a postdoc there as well. And his expertise is on efficient integration of machine learning and data analytics in the context of relational database systems. And like this is at the core of DuckDB as well. And today he will talk to us about the testing infrastructure of DuckDB in the spirit of DB tests. So the floor is yours, Mark.
Thank you very much. You did a better job of presenting my first slide than I could have done myself. So thank you very much. I think I will be able to skip it now. So yeah, my name is Mark, and I've been working on DuckDB for the beginning. I guess I made the first commit. I've been doing it together with Hannes. Started out during my PhD at CWI. We had some slack time and we're like, maybe we should build a database system. Seems like fun. Turns out it was very fun. And turns out it has, grown quite a lot since then, of course. So for those that don't know, just a quick intro slide, what is DuckDB? So DuckDB is an in-process analytical database management system. And our tagline that we use is generally, it's the SQLite for analytics. So SQLite, of course, everyone knows, but it's a transactional system. So it's very slow when you want to run analytical queries. And DuckDB aims to be like the SQLite for analytics. So essentially, it aims to be pretty similar to SQLite in some ways that I will talk about a bit more later, but with a focus on analytical workloads. It's a free and open source system. It's MIT licensed, so it's like really, really free. And we have a website. It's pretty actively used currently, yeah, very exciting. All right, so when we developed DuckDB, when we started developing DuckDB, one of the systems we looked at the most was SQLite, and mostly because we just really liked it. And also because it's the most used system, database system on Earth, of course, but also because we just personally really like the system. And that's also where our slogan comes from, of course. We got a lot of inspiration from SQLite. Namely, DuckDB wants to focus on the same sort of aspects that make SQLite a very nice system to use, which is that it's extremely robust, it's very easy to install, and it's very easy to use. And we always strive for DuckDB to have these exact same properties. There's, of course, one big difference between the two systems, and that is that SQLite is focused on transactional workloads, which are usually consist of like many simple queries, and DuckDB focuses on analytical workloads, which is focusing more on like a few complex queries. And it turns out that there is this kind of difference there, where because these queries, they are very complex, they usually involve like various different aggregates, window functions, even like CTEs or recursive CTEs. They kind of require quite extensive functionality for users to be able to express their like desired analytical tool chains, for them to be able to get their results. And in order to accommodate for this, DuckDB aims to be a batteries included system, which I think is a big departure from SQLite, which aims to be more of a minimalist system. So what are those batteries? Well, for example, DuckDB aims for like very complex SQL support. So not just like select from where. It also aims to support all of the more, let's say, esoteric SQL features like window functions, recursive CTEs, correlated subqueries. And it doesn't just aim to support them, it aims to support them fast. So it wants to be like efficient at executing these things. We have types, which is already a big departure from SQLite. We have, of course, like decimals, sure, timestamps, but also complex nested types like structs, maps, JSON, lists, arrays, and all that good stuff. So we have like a big long list of many different types. we have many functions, we have aggregates, we have like a wide array of window functions. We have readers for various formats, including but not limited to Parquet files, CSV files, Pandas data frames, R data frames, Arrow, and a few others. Besides, of course, our own internal format. We do like parallel query processing, which is already like a big sort of engineering feature. Like it tends to complicate things somehow, parallel processing. And we do things like time zones, thanks to Richard. And we have support for like complex collations and such, and many more. Essentially, DuckDB does a bunch of different things. And that sounds nice, but there's this kind of balance there that as you add more features, you kind of have to add more code, and more code kind of causes more problems. Surprisingly, that's why I'm here at DB Test and why this topic interests me so much. So there's this nice quote from Dijkstra that says, if debugging is the process of removing software bugs, then programming must be the process of putting them in, which I think is a very funny quote. And also there is like an element of truth to it, right? So the way that you might view system development, if you had like let's say you had a measure of robustness, I wouldn't even want to think of what this would be, but let's say you had a measure of robustness. As time goes on, you have this sort of like spikiness where when you do debugging, you remove bugs, which increases the robustness. When you do programming, you add features, you kind of decrease the robustness. So robustness and feature development, they're kind of at odds with one another. Yet we really, really, really want to have both. So what can we do? Well, testing, hey. So testing is great. Allow me to preach to the choir for a moment. Of course, at DB Test, everyone loves testing, very surprising. Well, testing is very important because, well, you kind of need to do testing in order to verify that the code is correct in the first place. Regression testing, it's very important because it prevents bugs from reappearing, which they kind of have a tendency to do so otherwise. And testing also allows you to catch bugs before they become a problem. So if you do proper testing during development, you may not need to deal with an angry user shouting at you that there is a problem with their system, which is not great. So there's this nice quote from Don Knuth, which says, beware of bugs in the above code. I've only proved it correct and not tried it. And I think this relates very well to testing and why it is necessary. So yeah, testing is great for robustness, but it actually turns out to be very important for feature development as well. Because if you have a good test suite, it allows you to add new features, optimize your code, or even refactor without breaking existing functionality. With like a bit of asterisk there, it allows you to do that without breaking functionality that is tested. There is still, of course, potential problems there. If you break something that was not in the test suite, you may not realize it was broken. But it is an extremely powerful thing when you have a very complete test suite, because you can be sure that even as you are adding features, even as you're doing like code optimizations, even as you're doing like complex refactorings, your system still stays like within some sort of, it stays robust, let's say. And that's of course very important if you want to maintain robustness while developing features for a system. So, of course, testing, it's important for software development in general, but I would argue even more so for database. So what makes databases so special? Well, the way I view database system development is that it's kind of a double-edged sword. So on the plus side, the functionality of database systems, it's well-ish defined. So SQL, it's a standard, sort of, and changes in requirements that deviate from that standard are unlikely, at least from like a functionality perspective. Of course, I say sort of because while there is a SQL standard, there is a lot of, it leaves a lot of room for imagination, let's say. There's a lot of implementation-specific stuff in there. And of course, systems generally have system-specific extensions that can be very, very significant as well. So what does that sort of standardization allow for, though, is that you can just write a bunch of SQL tests once and they will be valid forever, which is super useful because one of the problems that you face when you test in regular software development is that you write a bunch of tests and then your user comes to you and says, oh, but now we need to do something completely different. And suddenly your entire test suite is useless. In a SQL system, you don't really have that problem. You can just be pretty confident that when you write these tests, they will be valid. Of course, there's some caveats, and sometimes you will need to rewrite tests, especially for custom extensions. But there is like a large fraction of your test suite that will just be like locked in place. Another great part of this is that you can adapt tests from other systems that have been like battle hardened, that have like developed large test suites over the years, such as SQLite or Postgres. And that really allows you to get like a big jump start on finding potential problems in your system, because you can test against these existing implementations. Another big advantage of this is that there is a source of truth. So you can look at, if you don't need to guess what a specific SQL query should return, again, asterisk, given that it complies to standard, yada, yada, you can look at the standard, or you can just compare against existing systems or do a mix of those. And that's also very nice from a development perspective. On the flip side of this, there is the fact that they have very high expectations of database systems in terms of robustness. And that's, of course, not, that's not without reason, right? That's actually totally valid. I myself would have that as well, because you trust these database systems to safeguard your data. You make decisions based on the results of these analyses. You get like a bunch of graphs and you decide, should we do this or that? And if the analysis is wrong, you make big mistakes. Or if you run a transactional workload, if you lose data, that may be extremely damaging to your company, to your bottom line. So of course, database systems, they need to be robust, right? It's kind of like a core tenet of the field, I would say. But it don't just need to be robust, they need to be robust in extreme scenarios. So not just does your system need to work in like the happy scenario where you have infinite RAM and you're running like a 1 gigabyte data set on a computer with 300 gigabytes of RAM. They need to be robust in extreme scenarios as well, such as when you don't have enough RAM to fit your data set in memory, or when you have like power outages. And if they are not, like if your database corrupts data because of a power outage, you will get people complaining. And again, they should be complaining, right? Database also need to be robust against many different inputs. So it's not just that they need to be robust on one workload, they need to be robust against for various workloads, various query workloads on various data distributions. And that's not just in terms of correctness, that's also in terms of performance, right? They don't need to be just correct, they also need to be fast. And I think this kind of complicates the system development landscape a bit. All right, so that is why testing in database systems is useful, and I would say even critical. How do we do it in DuckDB? Well, I had to look back at the very first version of DuckDB back in 2018. This was like a few days after the first commit, and I found the very first test in DuckDB. This was written using like the C API. It was like manually, we didn't have like any test suite. It was just like we checked the return values, we printed stuff, like there was no like CI yet. Like this was like day 3, right? This was like our first attempt at writing a test for DuckDB. Of course, we ran into some problems with this. Well, actually, it turns out a big problem was just using the C API, because if you have a failure, you don't run your cleanup code at the bottom, and then you get memory leaks. And that turned out to be very annoying, because you would get a test failure and a bunch of memory leaks, which would just clutter your output. So that was not great. And of course, you really need to reduce the amount of boilerplate in your tests, and having this and not having a proper test suite for that leads to a lot of repeated boilerplate. And that really inhibits the writing of tests. And that's something you really want to make as easy as possible. So after that, what we moved to was using the Catch framework, which is a very nice C++ testing framework. I can recommend using that. And we started writing tests against our C++ API. And we kind of have this mix of SQL tests and internal component tests. Here are two examples of such tests. But there were still some problems. So every test written like this needs to be compiled and linked. And that's kind of annoying because if you change a header, suddenly you have to recompile your entire test suite. And this turns out to be quite problematic when you have many, many tests. And you really want to have many, many tests. So again, this is one of these things where you do not want any sort of, you don't want the system to get in the way of you writing tests. There's also, of course, the thing that if you want to add a test, you have to add it to the CMake, you have to recompile it every time you change it. It's just, it makes writing tests more annoying than it should be. And again, you want like really low friction on these things. Another even bigger problem were these like isolated component tests. So because DuckDB was such a young system at the time, it's still quite a young system, but at the time was like was like at its conception, right? We were refactoring things all the time. We were like, we would make a binder and we'd figure out, hey, this doesn't do what we want it to do. We need to like rewrite this code. And there's one big problem if you use all these internal tests, especially with a new system, and that it's kind of, it locks you into implementation details. Of course, not really. You can, if you change the internals, you can also change the tests, but it creates a lot of unnecessary friction to that, to the point where you will probably be a lot less inclined to do these rewrites, and these rewrites may be very much necessary. They may be like improving the system or turning like something that used to be an edge case into a common case. Like it's very much at the beginning, especially at the start of a system, you really want to do these refactors once you learn new information about requirements. And internal tests make this a lot more difficult. And we also kind of figured out they're not really required for a database system because you have the holy grail, which is SQL, right? So that's what we use currently. So this is what our tests look like currently. It's the SQL logic tests, which are used by many different systems. They were originally created by the SQLite authors. And it's kind of like a very quite simple, straightforward file format, right? Like you can read this and you can immediately tell what's going on. So you just kind of tell the system, okay, I have this query and I expect this result, or I expect a query not to fail or to succeed. And it's very nice because these are interpreted tests and you don't need to recompile anything. You can add as many as you want. There's no like big penalties for adding a new test. And once, if we change our internals, these tests will never need to change, right? Because they just do SQL. So yeah, SQL tests, amazing. But they do have their limits, of course. So there are things that are hard to test with just SQL correctness tests, which is what the SQL logic test is. One of these things is internal properties. This is something that's very easy to test if you have internal component tests, but very difficult from a SQL test. You can only test like the end-to-end thing, which is usually what you want to test anyway. But there are some internal properties that are useful to test that may not be very easy to test from within just SQL. Another thing that's hard to test is optimizers, because optimizers have this sort of property where if an optimizer works correctly, it does not change the result of a query. So how do you know the optimizer even did anything, right? Because that's the expected case. It should not change the result of a query. Otherwise, your optimizer probably has a bug. Well, probably, certainly. Another thing is performance. So if you change, like these logic tests are great for detecting correctness, but how do you test performance? So let's focus on these one by one. So the internal properties, how do you test internal properties using SQL tests? Well, what we have kind of added into our system is this form of what we like to call drive-by testing. And the idea is that we have this massive test suite of millions of queries. Can the system not just verify the internal components we care about while it's running, like the internal components that are kind of like hard to test through just SQL? And the way this works in DuckDB is that there is a verification flag that is enabled at the top of most of these tests. So you have this like pragma enable verification, and that will enable the system and to enter verification mode, which will verify a number of different properties. One of these, which I think is extremely powerful, is that it will run each select statement twice, once with the optimizer enabled, and once with the optimizer disabled. And then this is extremely powerful because it allows you to, just by looking at the system itself, like you don't even need to know the answer to a query, right? Just by looking at how the system behaves, you can figure out if there's a bug in your optimizers. Because if the run without the optimizers produces a different result from the run with the optimizers, then, well, your optimizer screwed something up. Or what has also actually happened sometimes is that your optimizer fixed something. So we do sometimes find bugs where there is a bug in the unoptimized version that then the optimized version does not have. So that's something that's even more difficult to find in a normal test because you would always run with optimizers enabled. And those bugs that get fixed by the optimizer may also not always get fixed by the optimizer, right? This may be like maybe a bug in a cross product that you would normally not run, but now you run because your join order optimizer is disabled, and then and you may not have as many cross product tests as you have join tests, probably. Other things that we find very valuable to verify is functions that round trip. So for example, DuckDB has a bunch of functions that do like deserialization of structures. It does like copying of queries, of expressions, those sort of things. We have like a toString method. And these all, they kind of round trip kind of naturally, right? Like if I have a select query and I do a copy, I should get the same select query. If I serialize my select query, I deserialize it, I should get the same select statement. If I do a toString and I run it through my parser, I should get the same select statement. That's not always true in all systems, of course, but that's a property that DuckDB has, which is very powerful and that we actually verify. So what we can do with this verification is that we just do all these things. We do like a toString, pass it through a parser, we create a copy, we create the serialization, deserialization, and we just run the query a bunch more times. And again, we do this result comparison where we say, okay, if we run the query again on a copy, it should return the same result. And these things, they turn out to be very hard to detect otherwise, but this internal verification, it just finds problems immediately. Like you have a bug in your toString, it's immediately done. Like immediately finds it. You forget a field in your copy method, immediately finds it. And it just like adding this solved like a bunch of different problems that were otherwise very painful to test. And it's all this drive-by testing. Like we don't just test these things on like a few select statements, right? We test this on millions of them. And that is where like this immense power comes from. And it gives us a lot of certainty that these methods are correct and stay correct even as we add new things, right? Because a big problem with like a copy method is you add a field, but you forget to add it to the copy. Now it breaks. Using this, we just immediately detect it using our test suite. Other stuff that's kind of useful to do this verification is like verifying internal state of intermediates. So these things you probably always want to do in debug mode anyway, like you want to have a bunch of assertions in your code, of course. But during verification, we generally don't care as much about performance, like even less than normal debug mode, and we just verify. So we check like, okay, are all the strings UTF-8 valid UTF-8? Are there like null bytes in strings? Because there shouldn't be. Are like things like if you have arrays, are all the list offsets and lengths, are they all in bounds? If you have like a selection vector, is all of that in bounds? And that turns out to also be very useful for finding any sort of internal error that may otherwise kind of like have snuck through somehow, right? Also statistics verification, super useful, very powerful, where we have a bunch of statistics, we propagate that through our query plan, so every expression actually has statistics. You want to make sure those are correct, because if they're wrong, your optimizer will make wrong decisions, and those can be kind of like subtle wrong things. But if you just look at the actual result and you compare it to what the statistics say it should be, you can very quickly and very accurately pinpoint like, hey, this thing is wrong right here. And that's super powerful. And so kind of the overarching theme of all this like internal verifications is that for all of our tests in our test suite, we kind of just want to get more bang for our buck, right? We want to extract the maximum amount of value from our test suite. Because we have all these queries from various systems, we have our own test suite, and we want to find as many potential problems as possible in order to keep the system as robust as possible, right? There's of course a downside. The test gets slower with this verification. The main problem and why we don't just run all the tests is that if you run an unoptimized version of a query plan, and you have like an implicit join. Of course, an implicit join is actually a cross product. And if you don't have like a push down optimizer or a join order optimizer, you run an actual cross product, and that turns out to be excruciatingly slow for anything beyond like a few thousand rows. So that is like a downside, but generally we only run this verification for like smaller workloads where you have like a few hundred rows at most. And for this, it's very powerful. All right, then we have optimizer tests. Optimizers, like I mentioned before, they're hard to verify because the query should be correct with or without an optimizer. So how do you know if an optimizer has had an effect? Of course, you can do like profile. You can look at the performance, like has the performance improved? But that is like a bit more challenging. And then you have to write like performance tests where the optimizer has like a very significant effect. It's a bit more challenging. So what we actually had as an idea is, why don't we just check the explain output? And specifically, we look at the optimized plan only. Like we have this feature where DuckDB has different query plans. We have like an unoptimized plan, optimized plan, a physical plan. If we look only at the optimized plan, we can kind of check if the optimizer has had an effect by comparing the optimized plan of a SQL function that should have been optimized to what the SQL rewrite would look like. So to give you an example of what we do, for example, suppose I have an optimization. Well, we do have an optimization that says, okay, if I have a like expression, a like function that does not have any like special symbols, right? It's basically just an equality. So we should be able to rewrite it to an equality. What we can do is we can write a test like this, where we say, okay, I will run and explain twice, once with like the thing I want to optimize, that I expect to be optimized, and once with the thing where the optimization has been applied, right? Like with the equality. And if the optimizer does its job, these optimized plans should look identical because the like should have been turned into an equality. And what's nice about this is that we don't actually we don't hard code our explain output here. We just verify that it's the same as another one. And that is nice because again, explain, it is like not standard, it is system specific. And from time to time, you might want to change your explain output, but by doing it like this, you don't break these tests even as you change your explain output, because this property should still hold. It will only break if the optimizer fails to do this. Unfortunately, that's not always possible. So sometimes you just can't do a SQL rewrite very easily. In those cases, we also have tests where we inspect the plan directly. And what we actually do is we don't just plop the whole plan in our tests. We do like a regex on the plan and check if certain nodes are present. And the reason we do this is, again, because we don't want all of our optimizer tests to break in case we change anything in the explain. Kind of like detach the tests as much as possible from internal implementation details. Unfortunately, these ones, they still do leak something like the empty results. So for example, here, I have an example test where if I have a between clause where the first element is bigger than the second element, this will always return false or null. So I can prune this entire plan, and this should just always be an empty result. So what I do is I look in my explain tree and I check, hey, is the empty result node there? Has the plan been pruned? All right. So that is testing in DuckDB. How do we utilize this during development? So of course, like I think everyone here does, we rely heavily on test-driven development. And the way we cater towards that is that we try to make tests very easy to write and very easy to run. And we encourage people to write many tests whenever they implement a feature, whenever they fix the bug. And we also encourage people to avoid writing only like happy path tests, right? Where you just test like, oh, this is the thing that works, but you don't test any of the edge cases. We really try to have people think of as many corner cases as possible. And afterwards in code review, we try to think of more corner cases so that we really can try to capture as much as possible. Of course, something sometimes slips through, but we try to already from the very beginning capture as many of these potential problems as possible. So our development, it always happens in forks. And one of our sort of holy doctrine rules is that the main branch of DuckDB should always be stable, with as like our target that we should be able to create a release from the main branch at like any point, which means that ideally the main branch always passes the continuous integration checks and it can always be run. And we actually kind of do this release thing because we, on every single commit that gets pushed to the main branch, we create a pre-release. And that pre-release, people actually tend to use, like that's actually gets quite some usage. We rely super heavily on continuous integration or CI. That's also everyone should, I think. CI really allows you, like it ensures that your system remains stable. And in our experience, kind of anything that's not automatically verified by CI will eventually be broken. That's kind of like a rule of thumb that we have encountered again and again and again, where we really try to verify as much as possible in the CI. And whenever we fix something, we try to make sure it doesn't break again. So for example, if we, let's say we fix all of the warnings on our Linux compiler build, something like silly like that, right? We add that to the CI and say like, okay, there shouldn't be no more warnings on Linux. Because if we don't, then in 2 months, someone will come along and create a warning. And every time this happens, like it's really like critical that you have your CI as complete as possible in our experience. So of course we do this. We have a very extensive CI suite that currently consists of 79 workflows. And of course we have workflows that verify like the basics, right? We verify that all the tests pass, we verify compilation, but not just compilation on one machine, we verify compilation on many different setups. So we do like compilation on different operating systems using different compilers. We do like checks for making sure there's no warnings. We have tests for all of our like client interfaces. And one of the things we also do is that in our CI, we verify code style and code formatting, which is also quite powerful because and it's also quite nice as a code reviewer, because it means you no longer need to complain about like code style in PRs, right? Because if someone like uses the wrong casing for a function that's like not up to what the project does, the test will just fail. And if the test fails, it will tell them like, hey, fix this here. And if they don't fix it, then well, you're just not going to merge it. You never need to like point people to these things, and it will never be broken, which is also very important. Aside from that, we also run our test suite and try to like push out more, like squeeze the test suite for more bugs by running it in different configurations. So one thing we do that's very powerful for a vectorized system is that we run DuckDB using different vector sizes. So what does that mean? Well, DuckDB is a vectorized execution. It has a vectorized execution engine, which means that during execution, vectors flow through the query plan, right? So those vectors, normally they're like a few thousand elements long, but it turns out that there are quite a few bugs that we found before where that would only occur if you had like more than a few of those vectors, so a few thousand elements. And it turns out that many of our tests do not have a few thousand elements. They have like 10 elements. So those bugs would be hidden in our tests. However, now we have expanded our test suite to run with a vector size of 2. And that means that any of those small tests also actually uncover this behavior and really like finds quite some bugs just early on. Other things that we test is that DuckDB supports both an in-memory and a persistent backend. So we test like all our tests with both that. And we also run, of course, all of the sanitizers. So of course, the address sanitizer, the leak sanitizer are very important, but we also run the thread sanitizer, which is extremely powerful. And again, like all of this is just to like push as much as possible, like squeeze as much as possible out of the test suite to like maximize the robustness of the system, right? We also run fuzzers in the test suite. And I'd like to talk a bit more about fuzzing in DuckDB. So there's been a nice story about fuzzing in DuckDB, how it first came to pass. So back in 2020, we already thought we had like a pretty robust system, right? We had like thousands of tests from various systems like SQLite, Postgres, hundreds of our own tests. And then this guy called Dr. Rigger came along and he unleashed his creation upon us and started furiously opening bug reports. Using SQL Answer, Manuel found around 80 bugs in DuckDB. And those were bugs that were not found using the test suites of the other systems, right? So we ran the SQLite tests. They did not find these bugs. We ran the Postgres tests. They did not find these bugs. And it turns out there's kind of this thing where database systems are complex, surprise, surprise, and each system has their own bugs. So while the tests from other systems are very helpful, they're not a silver bullet because there may be edge cases that another system does not have that you do have, right? So it may not be part of their regression test suite because they never encountered this issue because they don't have this issue, but you may have this issue because you have like a different optimizer, different execution workflow, what have you. And fuzzers, we have great experience with fuzzers. How it tends to work in our experience is they find like tons of bugs initially. Like you unleash a fuzzer on a system, it finds like 50 bugs. Of course, that depends, but let's say a large number. Depends on which fuzzer you're running. If the system has been fuzzed before, it finds many bugs. But there's this sort of like diminishing return there. So the way that I view it, at least, is that fuzzers, they have like a domain in which they find bugs. And after all the bugs that this fuzzer finds are fixed, there's not that many new bugs to be found. Of course, fuzzers are random. They can generate like crazy queries, but there's like usually a few like bugs that are found very fast or even a lot. But after that, the amount of bugs, like it kind of wears off very fast. And that's kind of why I think it's very important not to just run one fuzzer, but to run many different types of fuzzers, because these fuzzers, they have like different domains. So if you shouldn't just run SQL Answer, you should also run SQL Smith, because SQL Smith will find bugs, SQL Answer will not, and SQL Answer will find bugs, SQL Smith will not. So it's very powerful. You should run as many as possible, I think. Also, kind of a lesson we learned is that running a fuzzer just once is not enough, at least in a system that's evolving very fast like DuckDB. So it's not like you may kind of have this like sort of idea that, okay, I run SQL Smith, right? And I fix all the bugs it encounters, and then you have this diminishing return. It no longer really finds bugs. And then you may stop running it because it's not finding bugs. But in my experience, that's not a good idea because new code you introduce to the system should also be subjected to these fuzzers. Because while the existing code may have all the bugs fixed in the domain of the fuzzer, let's say, the new code has not been fuzzed yet, and it might totally have bugs that are in the domain of the fuzzer that the fuzzer will find. So when we first started fuzzing, we tried to just have like our separate machine. We have like this this cluster at the CWI, and we try to just put it on a machine, run a fuzzer, and it would just like fuzz. It would find bugs. We'd fix the bugs. And at some point, this diminishing return set in. It didn't really find bugs for like weeks. And the machine needed attention. Like the machines here, they are a bit brittle sometimes. The hard disk exploded, something like that. It didn't work anymore. And it just kind of fizzled out, unfortunately. Like we just stopped running it because, well, it wasn't finding bugs at the time. But after a while, those bugs that the fuzzer finds reappear again. So we had this kind of idea, okay, what if we just run fuzzers in the CI? We have to run CI anyway. So we don't have to like maintain another machine. But there's one problem with that, which is that fuzzers, they're unpredictable, right? So what tends to happen is that a fuzzer, it will find a bug in the system, but it will probably not find a bug that was introduced in a specific commit. It might, but it might also find a bug that was introduced 3 years ago. So you don't really want to like block merges or PRs or like fail CI based on the output of a fuzzer, because the fuzzer, very likely the failure of the fuzzer is not related to the actual code change. So we had this idea, what if we fuzz in the CI? So we just use our CI for that because, well, we are maintaining it anyway, but we just don't fail. So the CI just passes as long as there's no like internal fuzzer error. And instead what we do is we just take whatever comes out of the fuzzer and we just file GitHub issues. And so the fuzzer of Ducks robot was born. And this is what runs now in our CI. It currently runs SQL Answer and SQL Smith. We also run OSS Fuzz, but that's managed by Google. That's not by Fuzzer of Ducks. And what it does is, if a bug is found, it creates a reproducible test case based on the output of the fuzzer. It does test case reduction, and then it files an issue in our DuckDB fuzzer repository that we can then look at and fix without failing the immediate CI. The test case reduction is done using DuckDB. Eat your own duck food, after all. And the way this works is that we have this this function that's called reduce_SQL statements that we added just for this purpose. And what that does is it just does like a one-step reduction of a statement. So for example, suppose I have this select statement here. I can reduce this statement by one step by removing the from clause, removing an element from the order by, removing the entire order by, replacing the select list with like a null. And what we then do is we use this function to just continuously find candidates for reduction. We try to see if the fuzzer still, like if the test still breaks, if there's still like a problem. If it does, we update the current query with the like simplified one, and we just do this for a while or until we no longer find a problem. And this works very effectively at reducing the queries that you get from these fuzzers, which tend to be quite monstrous. So here's an example of a issue that was filed by the fuzzer of Ducks from a bug found by SQL Answer, where there is like a runtime error in our like strup time, I think. And you can see it's quite nice. You have like a very short reproducible script. Like here you go. The fuzzer has tested that this is reproducible. It has the error right there. You can just copy paste this into a test file and run it, fix the bug, and submit a fix. And the nice thing is the fuzzer of Ducks will also close issues automatically after they have been fixed. So you need to do like zero maintenance. You just get like free test cases. And that's super valuable because often like finding a problem, finding out why the problem happens, finding like a test case for the problem, that is like 90% of the work for fixing a problem, right? So having that done automatically, and all you need to do is like fix the problem. Usually it's something stupid, right? Not always. Sometimes you need like a more structural fix for this, but often it's a pretty simple fix. So it's very nice to be able to detect these things with a fuzzer, generate these test files as well. Another thing we run in our CI is performance regression testing. So like I said before, SQL logic tests, they're fantastic, but they detect regressions in functionality, but not regressions in performance. And it turns out performance, it's kind of a big deal for database systems. People care about performance. I mean, there's all these benchmarking wars going on, of course. People want their systems to be fast. So, of course, you can spend a lot of time optimizing a database system, but then you may hit a performance regression. So after you have optimized it and made something fast, the question is, how do you maintain that? How do you make sure you don't accidentally like ruin all of the stuff that you have worked so hard to achieve in your optimization? Well, we started doing performance regression testing actually quite early in the project. So in this initial version where we had like a separate machine running benchmarks continuously, it would like pull a new version, it would run a benchmark for each commit, and it would generate this nice history of performance timings and like these nice graphs. Looked very nice. It was very like a very nice visual thing, and was very useful as well because it would actually usually pinpoint the exact commits, like, hey, this commit is what broke the performance. And unless you have like someone that pushes like giant monster commits, usually the culprit is like pretty easy to see. So it was very powerful. The problem was, as you might guess, again, the machine broke. Like I said, our cluster here, it's a bit brittle, and you can guess the rest. You know, like we were busy doing other things at the time. It was also just like we were two people. We were building a database system. We didn't want to do also like sysadmin work, so we kind of just discontinued this at some point. So we have this new idea again. Like we like CI. What if we just run the regression tests in the CI? So our idea was, okay, we can just run a representative subset of benchmarks. So not all the benchmarks, because we do have a lot of benchmarks, but like try to pick out something that's kind of representative. And then we fail the CI if a significant regression is found. And that turns out to be very effective because you can immediately see like, hey, what is the effect of these changes on my performance? Is it significant on any of these queries? And it's very powerful. And it's actually in some ways more powerful than our old setup because you are immediately notified of it rather than being notified of it after the code has been merged when it's already kind of like more of a step to fix it. There's one thing though about this, it's false positives. They're not very fun because you may change like some line and suddenly a regression test fails. And this turns out to be like kind of a problem if you run 250 queries on every single PR in like a CI box at some VM somewhere. You do sometimes get hit by false positives on like one of these, because even if there's like a 0.1% chance, it would happen like every 4 PRs, right? So what we kind of tried to do is minimize this by running many times in a loop. And only if like all of them regress, then we are like, okay, probably this is not random noise. So we're kind of like on the conservative side of this, where we very quickly say if the timing like kind of matches up, or at any point we're like, okay, this is probably not a regression, let's say, with the idea that if there's a significant regression, then this will find it. Of course, there's the side problem of what if you have a lot of very small regressions, but that's like, yeah, a problem for another day. All right, so I also promised I would talk about the future testing plans. So I've mentioned now how we do our current testing, or at least a part of how we do our current testing, but we still have plans for extending that, of course. So here's some quick notes. One thing we have been wanting to add is verification of result equivalent operators. So this is more about the internal verification of the system. DuckDB, like I guess most database systems, has operators that should be the same. For example, we have a nested loop join and a hash join. Now, if they work correctly, they should produce the same results, right? So one thing we've been wanting to add to our verification suite is actually looking at query plans and checking like, hey, are you running a join? If so, maybe we can try all the different types of joins. And that will be very nice because then you can immediately see like, hey, there's a bug in like this one esoteric join. And that especially is probably nice for things that like joins that are not very commonly tested, right? Because of course our hash join, that's probably correct because that's what the system used like 99% of the time. But maybe the nested loop join has like some edge case bug that gets hidden because we only test the nested loop join in like 1% of the tests. So extending the coverage of the test suite for those more esoteric operators is very powerful as well, and something we want to explore in the future. I mentioned before, I think we should run many fuzzers. I think we should also run more fuzzers. So I have been looking at integrating more fuzzers, namely the AFL++, I think is very promising. because from what I've seen, you can train this on like your test suite, which is kind of cool because of course, SQL it's very nice, but it generates queries from like some known set of things that it knows about, right? SQL Answer, amazing, but it generates things from like things you have manually programmed in there. And whenever you add new features, you may not be adding them to those fuzzers, or probably you're not adding to the fuzzers because that would just like, it would add a lot of friction to developing new features. But if you could automatically learn how to use those new features from your test suite where you should be adding them, again, everything needs a lot of tests, then the fuzzer would automatically kind of evolve to pick up those new features and may be able to uncover more bugs, especially with changes to the code. So I think that's very promising. I've also looked at CLI, which I think is very cool, which does this sort of like program analysis where it tries to find like edge cases, like it looks at like all the branches in your code and then tries to visit all of the different branches, which is super cool. And I think that would be very useful to test things like our input parsing, where you can go like, okay, can I generate like a bunch of different Parquet files using CLI that would trigger like a bunch of different edge cases within our Parquet parser or a CSV parser. So those have been meaning to integrate. I'm very excited about doing that. Another thing is that we are moving towards backwards compatibility in our storage. So like SQLite, we want DuckDB to be backwards compatible, starting from version 1.0. So we're currently in version 0.3.4, and we're going to 0.4.0 Monday. But after we're kind of working towards being backwards compatible. And what that means is that we want DuckDB to be able to read files created by older versions of DuckDB, right? So if we have like, let's say we have hypothetically DuckDB version 1.3, we want it to be able to read files created by version 1.2, 1.1, and 1.0. But how do you do that? Well, you could, of course, create a large collection of files that you have manually created. But again, like in the spirit of squeezing as much as possible from a test suite, you could use the test suite for this as well by having like a sort of separate step where you create a database and have that step run using an old version and then running the subsequent steps run using the new version. And that creates this sort of like automatic backwards compatibility testing that scales as your test suite grows, right? There's like some caveats to that, like what if your tests use features that are not supported by older versions? But I think it's very promising, at least, to be able to automatically generate these backwards compatible tests. Another thing we have been thinking about is destructive testing. And I think this is like a much larger topic that you can really do a lot with destructive testing. And there's a lot of like potential things here. So I think the simple types of destructive testing that we definitely want to start doing as well is like introducing memory allocation errors. Like what if your malloc starts failing? That is what SQLite does, for example. And I think that is something that's very powerful because it can find problems in your out-of-memory handling routines that you would otherwise never find. Another thing we definitely want to start testing is doing like hard crash / power loss tests, which is still like, we do some tests where we do like kill-9, but I think they're like maybe some room for improvement where you would maybe even run something in a VM and then kill a VM. There's a lot of interesting stuff you can try there to try to trigger like weird scenarios that may uncover additional bugs. Another thing that's cool would be like introducing disk or RAM errors. Like what if your call to read fails? What if bits get flipped in your RAM? I think that's like way out there. Of course, I don't think any system produces correct results or even detects that like bits in RAM flip, but it's like a cool thought experiment. Like how would you even start to handle that, right? So yeah, that's like for let's say the science fiction part of this future work. All right. So that was my entire talk. Thank you so much for having me. I'm super happy to be invited to DB Test, which is one of my favorite workshops. And I'm super happy to answer any questions from anyone in the audience, be it physical or virtual.
Thanks, Mark, for the great talk. Tilman, we have a question at Slack actually. So
yeah, we also have questions here. Maybe you want to read the Slack questions and we start with the questions
yes,
in the room.
so in Slack, so Jim Apple is asking, oh, sorry, the automatic window closing. So Jim Apple is asking, there are times when you introduce a change to a database system and you are willing to accept a performance regression. How do you manage that in the CI system?
So there is an override flag for where we can just merge changes if we really want to. So it's not like there is a hard limit. There are some people, namely me and Hannes, that can just always merge things even if they fail the CI. So that we will have to like consider on a case-by-case basis, right? You are correct. Sometimes it is perhaps necessary. Of course, ideally, we try very, very hard to avoid it. But if there is such a scenario, we can override this.
Hi, Mark. Thank you for that excellent keynote. Quick comment and shameless plug. I'm Suhail. I'll be talking about fuzzy data at 3 p.m. So I really appreciated your extensive section on introducing fuzzers. And it's something that I'm working on in the data frame world with the Modin team. But just popping back and asking a sort of like a very hopefully basic question. Since I come from the sort of the data frame world, and my understanding is most SQL systems have unordered WAG semantics for returning results. What is the best practice in terms of just very basically comparing two SQL result sets and verifying that they are the same, especially if you don't have record IDs or primary keys to do the matching between two result sets?
So that is actually a super interesting question. If you haven't used DuckDB before or interacted with it, one of our goals is actually to be kind of also usable as a data frame API. And because of that, we do not actually have these unordered WAG semantics, and we go through quite some great lengths to preserve insertion order. There's a switch for it. You can disable this as well. But we actually don't have these semantics. But there are some cases where there is ambiguity, right? So for example, if you do like a select star from table, it will give you the results in insertion order. But if I do it like in grouped aggregates, the result will be sorted by hash. There's no like fixed order to that, which I think is also the same in the data frame world. So what we do then is we generally just run a sort and then do so it's sort by like each individual row and then do the comparison. So.
Okay. Do we have more
Thank
questions?
You for the question.
There's one more question here.
Okay.
So I would like to ask, how do you or do you optimize such that you test certain parts when you only modify those certain parts, such that you don't run the entire test suite if you just have a very minor change?
So we do run all the tests, but there is like, you can choose which tests to run during development, right? You can do like things, you can run all the tests in a folder, you can run a specific test. So while you're actually working on a feature, what you would usually do is just run one test at a time. So like, this is the test I want to fix. But of course, once it comes to time to merge, we do run all the tests. There is some exceptions to that, which is that if you change things in our clients, we will only run tests for that specific client. So for example, if I change, let's say my Python client, I know I'm not changing the core system, so we will not have to rerun all the CI jobs for the core system. But that is like the only exception. If we change anything in the core system, it will run everything, because of course, making a change in the core system might also break the Python client. But the other way around, it does work. We can reduce some of the CI jobs. But yeah, generally, we just run all the tests anyway. Because, well, you need to know if something broke.
So we have actually one raised hand. Norman, if you have a quick question, maybe we can also take it.
Yeah, thanks.
Oh, sorry. Go ahead. Go ahead, Norman.
Mark, thanks for the great talk. So I think that's really great to hear about the war stories in DuckDB. I have a question. How long does your test suite, your full test suite run? I asked basically, you mentioned regarding fuzzing that there are diminishing returns on the test results. And also for tests in general, there might be tests that are better uncovering issues, whereas some tests basically always succeed. And there's this concept of risk-based testing, which focus on, let's say, the interesting tests. Maybe you can elaborate on that.
I think that's super interesting. So we do have a concept of different classes of test suites based on how fast they run. So we have a fast test suite. We have like a medium test suite and have a slow test suite. And usually during development, you would what you would do is you would first run one test, right? Because you're trying to fix that one test. Then you would run the fast test suite, which takes like a few minutes to run. Then you would run the slow test suite, and then you would have the CI run all the test suites on all of the machines. And that's kind of nicer because that's done in parallel over multiple machines rather than just on your one computer. I think it's super interesting optimizing test case as well. We have done at some point, Richard did like some plotting of test case times and like figuring out which tests take how long. And it's always something that's kind of in the back of our minds. Should definitely add this to the future work section, because I think it's something that's often overlooked and that is actually important, because of course, there's the saying like, it doesn't matter how much time a machine takes, but that's only true if there's not a person waiting for it, which does happen with testing a lot. So I think that's super interesting as well, to look into like more test case reduction and such. So thank you for your question.
Is there time for one more question, or are we out of time?
Yeah.
Okay, yeah.
Quick, we can, and in the meantime, Mark, can you maybe unshare and the next speaker shares in parallel? Yeah.
Yeah, my question is really great talk, by the way. Really interesting to see. We do a lot of similar testing at Cockroach Lab, so it's fun to see kind of the similarities and differences. One thing that we also do is kind of automatic issue filing for failures for the cost fuzzer type tests. And what I find is that there's a lot of kind of false positives leading to some fatigue where we get a lot of issues filed from the cost fuzzer tests. And, you know, there are some gems in there, but often there's also, you know, rediscovery of the same issue over and over again, or some kind of, you know, test infrastructure issue. Do you have any strategies for kind of handling this kind of fatigue of multiple issues getting filed from the cost fuzzer tests?
Yeah, I think that's very interesting. We do, like our fuzzer does try to do some basic duplicate elimination, but it doesn't always work. As you are aware, it's so like the same bug may pop up in different scenarios and different things. So you do get like duplicates issues. I think, yeah, it's hard. There's always a balance to be struck there, right? Like how many false positives do you accept? I think we generally try to err like more on the side of currently, at least, on like if we know for sure it's a bug, it gets filed. If there's like any doubt or like we can't manage to reproduce it, then we don't file it, because that would because for now, like our engineer time is like we kind of prefer optimizing for that, let's say, rather than having them dig through tons of non-reproducible issues or issues that may not be issues at all. So, but yeah, it's definitely very interesting problem. I fully agree. So thank you for that question and comments.
Yeah. So with that, I guess I would like to thank Mark for the great talk once again, and maybe another round of applause.
Thank you very much.